Okay, welcome to this class. We're going to discuss symmetrical components and unsymmetrical faults. The basic idea here is to discuss unsymmetrical faults, but we cannot discuss unsymmetrical faults without understanding what symmetrical components are. That is the more reason why we start with looking at what the symmetrical components are, and thereafter we now go into understanding the unsymmetrical faults. So I'm going to introduce what the symmetrical components are, and then eventually we look at the unsymmetrical faults, and then later on I show you how to solve unsymmetrical faults using the Z-bus, which is basically the inverse of the Y-bus. Okay, so our topic of discussion is the symmetrical components and the unsymmetrical faults. Basically, I did introduce already. If you watch my YouTube channel, I've already discussed in most of my my previous videos. I discussed symmetrical faults, and I discussed some examples of symmetrical faults as well. But usually what, and in that discussion, I did go through it a bit in detail on the faults and what causes the faults. In most cases, the faults are caused by a number of things, one of which is lightning. Lightning is one of the causes, the highest causes of electrical faults in the system, where a lightning can strike on a conductor or on a transmission line and cause about a traveling wave that can hit the protective system. And that traveling wave is an overvoltage. So that overvoltage brings about the fault. Equally, we do get faults that come from switching activities in the system, switching stages, we call them. So these switching over voltages can also affect the system and cause about shorts. In other words, we also get what we call short circuits. This is where now you have two conductors connecting, or three conductors connecting unintentionally, which causes about what we call a short circuit fault. And this brings about a high fault current, which goes very high, in high magnitudes, and that fault current is dangerous to equipment. It can cause burnout of equipment. Burnout is where you have complete damage of an electrical installation or electrical equipment. And in other cases, you can have other sorts of damages. In some cases, the protective schemes would even fail to detect these high fault currents and allow that high fault current into the system. So in our understanding, when we discuss the symmetrical components, symmetrical faults, we understood that the symmetrical fault goes and occurs on all the three conductors of a line, meaning that the fault current is equal in all the three phases. In the unsymmetrical faults, rather, we have the situation becomes unbalanced, and in this unbalanced situation, because of the faults occurring in certain phases, not in other phases, it causes about an unbalance, and that unbalance now leads to the system becoming unbalanced. Okay, so what we see here is a balanced system. In a balanced system, we have the angles between the phases maintained at 120 degrees, electrical degrees. So you've got 120 degrees there, 120 degrees. So, and equally in a balanced system, the magnitudes of these phases, so VA, for instance, VB, VC, all these magnitudes are going to be the same. Whereas in unbalanced system, what you notice is that we have the phase angles are not balanced. So you may have a smaller phase angle here, for instance. As you can see, this is an angle that is way beyond 120 degrees. So this can be maybe 190 degrees. This can be 100. Differences in phase angles is one of the areas or the indicators of imbalances in the system. Excuse me, let me just bring this back. Okay, there we are. Okay, so this is the example that I'm talking about, where in an unbalanced system, what you have, first of all, the magnitudes are not equal. Okay, VA will not be equal to VB and probably not be equal to VC. And the phase angles equally are not equal between the phases. Okay, so theta 1, if we take this as theta 1, theta 2, these angles are not going to be the same. And this is an indicator of an imbalanced system. Now, we have Dr. Fortsk, who did a tremendous job in studying the faults in a three-phase system, where he developed the method of symmetrical coordinates. And this, according to his theory, is that if we have an unbalanced system, which we can see from here, if we have an unbalanced system, from this system, we have 3 unknown magnitudes, 3 unknown angles. And what we could do to calculate and see how this system is operating is that we could derive from this unbalanced system and develop 3 symmetrical components that will make it appear as though it's a balanced system. And these 3 symmetrical components are the positive sequence, what he called the positive sequence, the negative sequence, and the zero sequence, where each of the sequence elements is answerable to solving 2 of the unknowns. So this is the positive sequence is solving the one unknown magnitude, 1 unknown angle. The negative sequence is also solving 1 unknown magnitude and 1 unknown angle. Equally, the zero sequence is solving 1 unknown magnitude, 1 unknown angle. And these 3 components then can sort of show us, if we were to look at a balanced system, how we are able to determine the phase voltages that will give us a clear understanding of what is happening in the system when there is an unbalanced fault, a fault that causes an unbalance in the system. And because of this theorem, we are now able to calculate these 3 components, which we call the symmetrical components. So equally, his implication is that we're looking at unbalanced system, and we can create what we call symmetrical components. And with these symmetrical components, later on, we can utilize them to derive and solve the faults that occur in that causes unbalances in the system. If you look at these sequences, you see that you have the positive sequence where you have phase A, 1, having 120 degrees angle between phase A1 and phase B, and then you've got 240, so 120, because we go anti-clockwise, so we have 120 between A1 and C1, and we are going anti-clockwise in this case, so we've got 240 between A1 and B1, and so forth. But for the negative sequence, it's almost the opposite between the A and C phase, and then the zero sequence has got zero angles, as we shall see in the next slide. So what you see for the positive sequence, like I said, between the angle, between the phases, you've got, as we mentioned, you've got A, you've got B, and you've got C. So this A, if we take the voltage of this phase A, if we take, let's say 1, 1, 1, if we take the voltage of this VA1 to be the reference phasor, meaning this is aligned and there's no angle difference, so this is the reference phasor, then between A, phase A, and B, we're going to have 120, 240 degrees if we go anti-clockwise from there to there. Remember, we've got 120, 120. Add the two of them gives you 240 degrees. And this is why you see that the voltage at B1 is 240 degrees angle from the reference phasor, which is the reference phasor, which is VA in this case. But when we look at C, what we have now to see is we've got 120 degrees to C. So you've got 120 degrees from phasor A to C to C1. So this is what we get here. And we can represent the angle 120 degrees by the letter A. I will explain later on what this is in the next slide. So when we got the negative sequence, we've got the opposite happening in the negative sequence. So you've got the same A as the reference phasor. So if we take this as A2 as the reference phasor, what you have here is B2 and you've got C2. So for B2 now, what we have here is that our angle is now 120 degrees, which is this voltage here, VB2, being at a phase angle of 120 degrees from VA, which is VA1, VA2 in this case as the reference phasor. So we take this as a reference phasor, and then we have going to C, phase C, we take 240 degrees, okay, 240 degrees, and this is what gives us in reference to our phasor voltage VA2. For the zero sequence, like we said, there are no angles, so for the zero sequence we simply have these components, zero sequence components. VA0 is simply equal to, they are all equal to VA0. So VB0 equal to VC0. So all the components are equal to one another. So from the symmetrical components now, we are able to determine that if we are to find the components, symmetrical components, we can write these phase components as the addition of all the symmetrical components. So if we add the symmetrical components, we can then determine the phase components for A, which is A1 plus A2 plus A0. This is referring to the positive sequence. This is referring to the negative sequence. This is referring to the zero sequence. Okay? And wherever you see a 1 from now on, it's referring to the positive sequence. A 2 is referring to the negative sequence, and a 0 in the components is referring to the zero sequence. Okay, so let's assume we've got three sets of voltages, that is VA, VB, and VC, given. Therefore, we are able to determine, according to Fort's research, the phase voltages can be resolved in matrix format, where we have VA, VB, VC equal to the matrix multiplied by, that is a 3x3 matrix multiplied by a singular matrix of the components. So here we've got the phase voltages, okay, the phase voltages, and on the other side we've got the symmetrical components. Symmetrical or sequence voltages, where V0 is for the zero sequence, positive sequence, negative sequence variable. So the operator A, like I said, is a multiplier, which is basically explaining the rotation of a vector through 120 degrees in the anti-clockwise direction. So A is basically, if we, like I mentioned, our rotation anti-clockwise 120 degrees, that is the operator A, which is 1 at 120 degrees. And then if we square this, so if we move, we continue moving up to here, we add another 120, which becomes 240 degrees. That gives us, now we are squaring the A operator, which now becomes A squared. Okay, and that A squared component is now equal to 1 at angle 240 degrees, which is now us moving from the reference phasor 240 degrees to that other phasor. And these we can expand using the Cartesian coordinates, meaning 120 degrees will be cos 120 plus yod or j sine 120 degrees. This will give us minus 0.5 plus j or yod 0.866. Equally, the A squared operator is equal to 1 at angle 240 degrees, which is equivalent to cos 240 degrees plus j sine 240 degrees, giving us minus 0.5 minus j 0.866, or yod. I usually call this j, yod according to the pronunciation in the Greek alphabet. So do not be surprised when I call this yod. Okay, and then A cubed is going to be 1, and while we can also have A squared plus A plus 1, that will give us 0. So take note of these, because this is what we imply when we add these elements or the operator in our matrix. So this is our A squared, this is our A squared. You can see the diagonal elements here, 1 A squared, and then you've got the off-diagonal elements there as A and A. This is what we mean. These are the angles that we have for the matrix. If you now come to writing these equations in terms of the phase voltage values, so our phase voltage VA is going to be the sum of all the symmetrical components, that is the zero component, the zero sequence, positive sequence, and negative sequence voltage. Equally, the phase voltage for B, or B phase, you have V0 plus A squared V1 plus A V2. This is all coming from the matrix that we just looked at in the previous slide. And you have your VC equal to V0 plus A V1 plus A squared V2. And we can rewrite these phase voltages to be represented by Vp, which is just a column vector of the phase voltages. And then we can represent the symmetrical component voltages to be Vs, which is a column vector of the sequence voltages. So V0, V2, V positive sequence, negative sequence. Okay, this is the zero sequence voltage. And then the matrix A to represent now the 3x3 transformation matrix. So we call this transformation matrix. Okay, and therefore we can now, from our symmetrical components, our goal here is for us to be able to determine and find the symmetrical or the sequence voltages that we're able to calculate. And if we take from the previous analysis that our phase voltage then is equal to A by the sequence voltages, meaning that we can find our sequence voltages from here, Vs, can be found from our A inverse multiplied by our Vp, which is the phase voltage. And then when we take this now, the inverse of A, which will give us now 1/3. So it's just the reversal of the elements in our matrix, where we have now the diagonal elements to be A, 1A and A, and then the off diagonal are going to be A squared. And that gives us the inverse of the matrix A. And since the inverse of the matrix A multiplied by the matrix itself, A is supposed to be a unit matrix, which is simply O1s, then pre-multiplying this by the inverse then gives us the sequence voltages. And therefore, we can now determine and create an equation or equations that give us now the solution for the sequence voltages, which is in matrix format, V0, V1, V2 equal to 1/3 multiplied by the A matrix or transformation matrix, which is now coming from the inverse. So we have the A inverse. Okay, so this is the element we are considering here. The A inverse is what we have now in here. This multiplies by the phase voltages VA, VB, and VC. And therefore, once we determine the sequence voltages, it is pretty much easier for us to now determine the faults, as we shall see later on. Okay, so rewriting the equations now from the matrix, just expanding from the matrix, what you have now is that the zero sequence voltage, zero sequence voltage is 1/3 VA plus VB plus VC. The positive sequence voltage V1 is 1/3 VA plus AVB plus A squared VC. And then V2, which is the negative sequence voltage, is 1/3 VA plus A squared VB plus AVC. Then we can equally rewrite the same if we have our phase currents to be as follows. Therefore, our sequence currents are also going to be equal to 1/3 for the zero sequence, A1 IA plus IB plus IC, 1 over 3 IA plus AIB plus A squared IC for the positive sequence. And the negative sequence is going to be 1 over 3 A plus IA plus A squared IB plus AIC. And therefore, for the unbalanced system, we have defined the terms, the three terms of the balanced system. And once we have that, we convert the phase voltages to symmetrical components voltages or currents, and vice versa. And then in a three-phase Y-connected system, the neutral current, so if you have a three-phase Y-connected system where you've got now the Y connection, you have also the neutral connection, then you can determine the neutral current to be the sum of all the phase voltages. That is, if you have A, B, C, for instance, so you have IA, IB plus IC, which is the neutral current. And then the neutral current equals 3 times the zero sequence current. So this is supposed to be 3 here. So the neutral current equal to 3 times the zero sequence current. And so it's very interesting for you if you could also take a look at sequence impedances, because that is what, although I'll cover that in the next video, but the sequence impedances is what we determine now, we use to find the faults when we look at fault analysis. I will introduce briefly what, without the examples on three-phase faults, and then you shall see what I'm talking about. So here's a small example on symmetrical faults, and in this example, you are just being asked to find the symmetrical faults given the phase voltages. As you can see, the system is not balanced. Okay, you can tell from the angles are not the same, and the magnitudes are not the same. So this tells you that the system is not balanced. Okay, so in the example, you have VA, which is equal to 5 at angle 53 degrees, VB equal to 7 at angle minus 164 degrees, and VC equal to 7 at angle 105 degrees. You have to find the symmetrical components. What do we mean by symmetrical components? You have to find the VA0, VA1, VA2. These are 0 means the zero sequence components or zero sequence voltages. This is the positive sequence voltage, and this is the negative sequence voltage. From our equations that we had 1 over 3 VA plus VB plus VC, which is simply the addition of all the phase voltages that you have multiplied by 1 over 3. And from there we get 3.5 at angle 122. Since zero components are the same, so your VB, VC are all the same. You remember we had all the zero components being the same from that diagram. So VA0 is equal to VB0, which is equal to VC0 components. So the value that you find for VA0 for the zero component is equivalent to all the values. So there's no need for you to recalculate the other variable or the other component values in this situation. So next we find the positive sequence components. Okay, so for the positive sequence components, what you have is as follows. You have VA1, which is equal to 1 over 3 VA plus AVB plus A squared VC. So we get our VA plus our A, which is this component, which is 1 at angle 120 degrees multiplied by VB, and our A squared is 1 at angle 240 degrees multiplied by VC, and we get our component. Now, if you remember in the positive sequence, what you have is as follows. You have got A, you have C, you have B. This is in the positive sequence component. So you have the angle between A and B, which is, you can take it either as 240 degrees, or you can take it, if we go this side, which is now the negative direction, to be minus 120 degrees for us to get to B. So the next component now, since you found VA1, then VB1, you can take 1 at angle 240 degrees multiplied by the solution that we have found, which is, in short, we are saying VB1 is equal to A squared VA1. Okay, now that A squared, as I mentioned, you can also take it as simply minus A. Okay, it's the same. So you can go this way, which is the 240 degrees, or you can go to the minus 120 degrees to get to A. So in this case, this is also the same as minus 120, 1 at 120 degrees, which is this component here. And this is what we use to get now VB1 and VC1. Equally from here, we are going to C, which is just 120 degrees. Okay, from here to there, we get 120 degrees, and we get our component value for VC1 to be 5 at angle plus 110 degrees. For the negative sequence, we get 1 over 3 VA plus A squared VB plus A VC. So this is our A squared component, which is 1 at angle 240 degrees, and then we've got our A component there, and we determine our VA to be 1 over 3 VA plus A squared VB plus A VC. This gives us 1.9 at angle 92 degrees. Again, if I take you back to for the negative sequence, we have the following image there, where you have A, you have B, and you have C. So for the remaining sequence variables, this is why we are saying for the sequence that we are following for positive sequence is the ABC sequence. Okay, the ABC sequence. And then here we are following the ACB sequence, which is this sequence, which is the ACB sequence. Okay, and in the ACB sequence, what you have is for the second variable of VB2, you simply have plus 120 there, 120 degrees to get to B, and you multiply that by VA2 to get our solution to be 1.9 at angle minus 1.148 degrees. And then to get to C, similarly here we could take the minus 120 degrees approach, or the plus 240 degrees to C to get to C. So this is 1 at minus 120 degrees. multiplied by 1.9 at angle 92 degrees to give us 1.9 at angle minus 28 degrees. And so you have found all the sequence variables. Okay, before I move on to the next example, let me just clean up the board. Okay, so in the next example, you've been given, it's the opposite. In this one, you have been given the sequence variables. So you've got the zero sequence variable V0, the positive sequence variable V1, and the negative sequence variable V2. And you've been asked to find the phase sequence components. Okay? You've been asked to find the phase sequence components. So in here, we've been asked to find the phase voltages. Okay? So the phase sequence, which is phase A, phase B, phase C, what you have now is VA is 0 plus V1 plus V2. And this is what you get, which is 5 at angle minus 53. For the phase voltage sequence component VB, you have VB equal to V0 plus A squared V1 plus AV2. You obtain 7 at angle minus 164. And then for the C phase sequence components, you get VC, which is equal to V0 plus AV1 plus A squared V2, which gives you 7 at angle 105 degrees. So that is how you can now utilize these very equations to reverse solving your sequences.